In this video, we're going to cover low-pass filters. As we've talked before in the earlier videos, filters refer to a circuit we can design to block off certain frequencies from going through. And low-pass filter basically refers to a filter where it only allows the frequencies below a certain frequency, usually called the cutoff frequency, to go through. Now, let's go ahead and walk through. Here's an example of a low-pass filter. So you've got, this would be your input signal that is coming in, and you are actually looking at the voltage across the capacitor as the output. Now, this is in a phasor domain redrawn. So capacitors, this is the impedance of the capacitor, and is written 1 over SC. We remember we used to just write it as 1 over j omega c, and in this particular j omega is referred to as S, a shorthand for S. So that's what we got going there. Using what we learned, or what you have already seen in earlier videos regarding sinusoidal steady state phasor analysis, we can apply that. So we could say, okay, we got a current going through here, so we could do a KVL and find this I. So if I were to do a KVL and find the I here, it would be minus VI plus RI plus I over SC equal to 0. So that would be, and then if we clean it up, then we will find I is equal to VI over R plus 1 over SC. And then if you want to find V out simply is going to be I time 1 over SC. And if we solve that, we will find a relationship between, which is V out is equal to this quantity times VI. If you bring the VI under here, we'll get this quantity. Now remember, this is called the transfer function, and that's really what we usually plot to tell us what we are looking for. So now that we have this equation, we can kind of rewrite the transfer function in terms of j omega and clean it up. So here we have the magnitude for j omega, and here we have the phase for j omega. Now if you plot, as you can basically come here and plot it, you will find out that as omega increases, this is in the denominator, so j omega decreases. So you will see that it more or less goes along this curve. Now the question is, where does this pass band stop and where does the stop band start? So where are we going to say it's not passing, or where it's passing the frequencies through? So where is this point? The way we decide on that, it was discussed earlier, but we'll go through it here again. The way we decide where this point is called the half power point, in addition to being called the cutoff frequency. Now, if you remember, h of j omega is voltage over voltage, and we know power is square of voltage. So if we want to find out where the half power is, then we have to say that h of s has to be equal to 1 over square root of 2 of h max, or whatever the maximum is. Now in this particular case, we know the maximum is equal to 1 because these are passive filter. Output can never be bigger than input. So the maximum value at h of s is going to be is going to be 1. So if that is 1, then at the omega c, h of s is 1 over square root of 2. That's how we find omega c. So we plug in omega c in this equation, and then find the magnitude of it has to be equal to 1 over square root of 2. So if you do that, here is exactly what that's been doing. We find that omega c is equal to 1 over square root of 1 over RC. So this is referred to as the cutoff frequency, or as we said earlier, is the half power point. You can also plot the theta, but we're more focusing on the amplitude at this point. And for all low pass filter, regardless of how we design it, always you can use h of s is equal to the cutoff frequency over s, and remember s is j omega. So as frequency changes, this is the equation that describes the low pass filter, and the cutoff frequency is basically where the half power point is. Now this is one way of building a low pass filter, putting a resistor, putting a capacitor here. As the frequency goes up, the resistor here drop, therefore the voltage drop. Another option is to use resistors and inductors, and more or less the same process. So if we use resistors and inductors, you notice that we take the V out here. Same idea, you can do a KVL, clean it all up, find the V out over V in equation, and you'll end up with something like this. And then to find out what omega c is, we'll set this magnitude of h of j omega at omega c equal to 1 over square root of 2, and we will find that. Now notice R over L was the time constant for the LR circuit. So that's kind of coming back to the cutoff frequency or half power point. Again, this is the cutoff frequency or half power point. And then omega c is equal to this. Notice the circuit is different. It's an RL circuit, where this was an RC circuit, but the end result equations are exactly identical. The omega c is calculated differently. For LR is R over L, and for the RC circuit is 1 over RC, but as far as h of s equation is concerned, is exactly the same, omega c over s plus that. So there you have it. This is the RL, and this is the RC. So that brings us to the end of low pass filter. Of course, somebody gives you a cutoff frequency or gives you what resistors or capacitors, you can design a circuit for them based on simply these two equations here and these two equations here, whether they want an RL or they want an RC. Our preference typically, if you have a choice of whether, if choice is up to us as engineers, we like capacitors better than inductors, just because they're a little easier to control and they cost less. Typically they use less raw material.